right, okay, continuing example 2. Here's our differential. I've taken this differential and I have factored it. Notice the numerator has been factored. Excuse me. In factoring, I can then very quickly note that when y is equal to 4, this part of the differential is going to be 0, which makes the expression 0, which means that any of these slopes in here, where the y value is 4, all of those slopes are 0. Also, when excuse me, y is equal to 0, okay, so when y is equal to 0, same thing happens. This part of the numerator is equal to 0, makes the entire thing equal to 0, makes all of these slopes along here equal to 0. If y is greater than 4, then what's going to happen is that the numerator is going to end up being negative, because this part of the numerator will be negative, this part will be positive, so you'll get a negative slope, and then the larger y is, the steeper the slope gets. So up in here, you can see that as we get further up the y-axis, our slopes get steeper. And since our slope is defined merely by the y position, then we end up with these slope fields that have all of these kind of horizontal parallel slopes, if you will. In between 4 and 0, the pattern of the slopes is that they will all be positive. And as you get up here close to 4, you're going to get close to being 0. As you get down here close to y being 0, your slope is going to get close to 0. Directly in between here at 2, the slope will end up being positive 1. And then finally, down here, when y is negative 1, negative 2, negative 3, our slopes again are negative. They're negative because this part of the differential ends up being negative, this part ends up being positive, and again, as you get further away from 0, the slopes end up getting more and more negative. So with our slope field built, then we can do a couple problems. Problem A. In the original function, when I plug in an x of 0, the y is 1. So I can take and plot that point when x is 0, y is 1. So that's that point right there. We'll make that a little larger so we all can see it. All right, try again. That point right there. There's the point 0, 1. And then I just simply, from that point, follow the slope field, and it's going to end up going up. Now I have a slope of 1, and then my slope ends up being close to 0. If I'm going in the negative direction, the slope becomes more and more shallow, never getting less shallow than 0. And then, to answer the limit questions, so the limit of the function, right, so this orange is the function as x approaches infinity. This is going to be 4, and as x approaches negative infinity, this is going to be 0. B. We're going to start at 0, 6, which puts us up here. And as we go to the right, we start with a slope of 1. And as we get closer down here to 4, the slope is going to get shallower towards 0, asymptotic to 0. So it's going to come down like this. And as we go to the left, it's going to end up going up like this. The limit questions then, as x approaches infinity, positive infinity, the slope, the function rather, the function approaches 4. As x approaches negative infinity, the function is going to approach positive infinity. Third question, C. We're going to start at 0, 4, which puts us right here. As we go to the right, it's just simply a horizontal line. As we go to the left, again, horizontal line. Limit as x approaches infinity, 4. Limit as x approaches negative infinity, also 4. Last one. Start at 0, negative 1. Puts us down here. So we go to the right. Very quickly, the slopes get steeper and steeper and steeper, but negative. So we end up like that. As we go to the left, the slopes get more and more shallow till we get to pretty much asymptotic to 0. The limit as we approach, as x approaches infinity, is negative infinity. Okay, not a very good infinity symbol. That's infinity. And the limit as x approaches negative infinity is 0. All right, turning on to the... Okay, so example 2 was a qualitative approach. Right, qualitative because in example 2 we used a slope field to look at sort of the flow of the function. To do example 3, we are going to go back to the quantitative approach. Right, so I'm going to walk you through the steps that we're going to need to do to find the specific function that has a slope of y squared divided by x minus 8 times x to the third y squared. In particular, I want to find the function that goes through the point 1, 3. So the first thing we're going to do is I'm going to take this and I'm going to factor out the y squared. Don't you wish you could write as quickly as I can? The second step I'm going to do is take and get all of the y's onto one side and all of the x's onto the other side. So we're going to take this y squared and put it over with the dy. We're going to take the dx and put it over on the right-hand side of the equation. And poof, there it is. Notice that to get the y squared over onto the left side, I divided both sides of the equation by y squared, and dividing both sides of the equation by y squared is the same as multiplying both sides of the equation by y to the negative second. And then the next step is to take the integral of both sides of the equation. Poof, there it is. And then the next step is to take and multiply everything through by negative 1, and that's going to make this positive, that's going to make this negative, that's going to make this positive, that's going to make this over here, make the constant negative, but once again, it's just a constant. We don't know what it is, so it doesn't make any difference whether we call it negative c or 2 times c. So we're just going to leave it as the constant. And then finally, since this is 1 over y, then we're going to take and do the reciprocal of both sides, which looks like that. Oops, almost like that. I forgot a negative right there. And then the next step is to plug in our point that we have. So when x is equal to 1, y is equal to 3. So wherever we see an x down here, we plug in 1. Wherever we see a y, we plug in 3, which gets us here. And then we'll do some quick simplifying, and I'm going to stay with you this time. So this is 1 over. This is the natural log of 1, which means that we're looking for the exponent that gives us 1 when we put the exponent on e as the base. So e to the what is going to be 1, which would be 0, and then it's the opposite of 0, which is just 0. So this is 0 plus 2 plus c. And then, so this is 2 plus c. You can, different people do this different ways. You can cross multiply, which would then give you 3 times 2 plus c is equal to 1, or 6 plus 3c is equal to 1, or 3c is equal to negative 5, or c is equal to negative 5/3, which then, putting this all together, gives us this right here. Okay, so just as a way of review, here's the question to think about. So we just went through all of this work. It all feels very algebraic, and we end up with the answer back here. We don't want to lose sight of the big picture here. The big picture being that we started with a slope. So this is the slope, and the slope is described with this pattern here. And that slope came from this parent function. This is the parent function. And it's a very particular parent function because we're looking for the function that goes through the point 1, 3.